Okay, kids. I'm out again. All I did is just get worse over the weekend. So hopefully my emergency vitamin C stuff kicks in soon, and yeah. So hopefully I'm back tomorrow. But yeah, I'm still sick. So here's another video. Today I want you to watch this video and take notes. And then the rest of the time, I'm gonna give you to work on your homework 2.3, which is the one with the forces word problems. So yeah, I know that guys are gonna probably get stuck on a couple, but I believe in you, and I'm pretty sure that you guys can do all of the problems based on what we've talked about so far. And this time, I'm not gonna leave a key with the sub because on Friday I was notified that there were some what's the word? Uh, just some shady business going on with people taking pictures of the key with the cell phone. Kind of defeats the purpose of having a key if everybody has the answers. So anyway, there's no key this time. So for those of you that use the key correctly, I'm sorry, and y'all will just have to just do without it. Okay, so what this video is about is basically what we were going to talk about today is unbalanced forces and the F equals ma equation, and kind of take it just to the next level of, instead of just looking at boxes with random forces drawn on there, we're going to look at actual word problems. Okay, and so I know that 8, 9, and 10 from that worksheet on Friday were really hard. And the good news is that most vectors that you're going to deal with are going to be perpendicular and way easier than those problems. So that was just kind of more to stretch you and then actually prepare you for like what's going to come next, because most of your vectors are going to be easier. Okay, your takeaway from Friday is supposed to be that if an object is accelerating, which means if the velocity is changing, then there are going to be unbalanced forces behind it, and then if there are unbalanced forces, then we're going to use that the sum of the forces, or the net force, equals mass times acceleration to find that acceleration. So here's an example. Let's say a 77 kilogram person, which is my weight, or my mass, sorry, is standing on a bathroom scale in an elevator. And the elevator begins to move, and the scale reads 820. And so if you've ever been in an elevator, which everybody has, you know that when the elevator starts to move, you feel heavier than normal. Okay, so one, I want you to explain why the scale is wrong, because I don't weigh 820. And then two, find the acceleration of the elevator that is causing this error. Air quotes. You can't see me doing air quotes, but I am doing air quotes. So here's some important info. And see, I got a pedicure just for y'all when I took this picture of me on a scale. Important info is one, scales always measure normal force, which is the force coming up from the floor, which might sound really weird to you, but that's what they're measuring, is the normal force from the floor. And so if I weigh 77, or if I am 77 kilograms, then my weight is going to be 77 times 9.8, and so my weight would technically be 755 newtons. So I should be offended, and I should return my defective scale, because I am not 820 newtons, I'm only 755. But there is actually a physics principle behind this, and the reason why you feel heavier when an elevator starts moving. Okay, so if you think about it, if my forces were completely balanced, that means gravity and the normal force would be completely equal. Gravity is 755, which is my weight, and the normal force would also be 755. And remember that the normal force is what the scale reads. Is what the scale reads. And so if I'm just, go to the bathroom and stand on my scale, the normal force and the gravity force are going to be equal and balanced out, because I'm not, sinking into my bathroom floor, and I'm not shooting up out of the ceiling. So my bathroom scale reads 755. But if I'm on an elevator and we're moving upward and accelerating upward specifically, then I'm going to be unbalanced. And the only thing that's going to provide a force upward to accelerate me upward is going to be my normal force. So that means that while an elevator is moving, technically I, as a person, am being moved by the normal force, which has to be bigger. And because the scale reads 820, that's what I know my normal force is, because scales basically just show you normal force. So in this example, gravity is 755. Gravity. My weight is still 755, but the normal force and what the scale reads is 820 because I'm accelerating upward. Okay? So if I want to calculate this acceleration, I'm going to use that the net force equals mass times acceleration. And in this case, my net force is just the difference between 820 up and 755 down. So I'm going to subtract these two, and that equals my mass, which is 77 kilograms, times the acceleration. And so 65, which is 820 minus 755, gives me 65. Divided by 77 is my acceleration. So my acceleration is 0.844 meters per second squared, which is a good acceleration for an elevator. It shouldn't be that fast. You're not going to move that fast in an elevator. Or accelerate that fast, sorry. Okay, so here's the weird thing. After a while, the scale is actually going to go back to normal. Like I'm still moving up, but eventually the scale is going to start lowering, and then it's going to go back to my real weight, which is 755. But I'm still moving upward in the elevator. And so a lot of people had problems on the homework with the guy in the refrigerator pushing it, and it said to have the refrigerator move at a constant velocity, how much does he have to push? And almost everyone said more than friction. But if you want to have a constant velocity, I'm moving at a constant velocity. I know my grammar is not that great when I'm sick, sorry. If I want to move at a constant velocity, that means I have no acceleration. The only way I can have no acceleration is if my forces are balanced. And so I must not be accelerating. I can't if my forces are balanced. And so that means that my scale is going to be correct again. It's going to perfectly balance out gravity, but I'm still moving upward, but at a constant velocity, because that means there's no acceleration. So the answer to that homework question with the guy on the scale is that you can't push more than friction. If you're pushing more than friction on the refrigerator is going to accelerate. You have to put exactly in what friction is pulling back, and you will balance. And if you're already moving and you already have momentum or inertia, then you will continue moving at a constant velocity. So let's look at, this little vector is lost and confused. So let's look at an example from the homework that you're going to work on in a little bit. And so this is number 3, I believe, on the front page. Okay, it says a 7 kilogram ball rolls down a 17.5 degree ramp. Sorry. A, what is the acceleration of the ball? We're going to ignore friction. And then B, if the ramp is 2 meters long, how much time to reach the bottom of the ramp? Okay, so I'm going to draw a diagram just to help me visualize. And there's a ball on a ramp, and the ramp, it says, is 17.5 degrees, which we know is this bottom angle. Okay, and so to find the acceleration of the ball, okay, whenever they talk about ramps, almost all ramp problems are going to be FMA. And so if I'm going to use forces, I'm going to have to draw a force map. So here's my little ball. I'm going to draw gravity, okay, and I know my gravity and my weight is 7 kilograms times 9.8. So my weight is 68.6 newtons down. And I know that there's a normal force. That was my stray vector earlier. And it's perpendicular to the surface, so it's kind of like at this little angle because this is the surface now, okay? And there's no friction, there's no tension. There's really nothing keeping this ball up. And so these forces are not balanced, and so the ball is going to roll down the ramp, just like everybody predicts that it would. Right? If you put a ball on a ramp, it's going to roll. So it makes sense that they're unbalanced because the ball accelerates. Okay? So if I want to calculate acceleration, again, in my brain, I'm already thinking net force equals ma. And so here is my force map again, okay, of these two vectors. And so if I want to find the net force, just like on Friday, you're going to have to do vector addition. And so when I do a vector addition, I'm going to add Fn plus Fg, and I fill in the little bottom, and that's going to be my sum of the force. And yeah, it's just like a triangle, okay? And so if I want to solve for the sides of this triangle, I don't really care about the normal force this time. I mean, maybe a question starts asking about friction, and friction does use normal force to calculate, so then maybe you would need to have normal force for that. But right now, I just want my sum total net force, which is this bottom side, okay? And so this triangle, though, right now, I can't do anything. I just know one side, but I do know that this bottom angle right here is a 90-degree angle, okay, because the net force is actually going to be down the ramp, okay, which it shouldn't surprise anybody that the net force is down the ramp because the ball will accelerate down the ramp. So this is a 90-degree angle right here. And then, as we talked about last week in class, which a lot of you, I think, missed because a lot of your mastery checks indicated that you missed this fact, is that the angle between the normal and the gravity force, Fn and Fg, is always the same angle as the ramp itself. And so the ramp itself was 17.5, so this angle up here is 17.5. Okay, so now I have two angles, one side, I can solve it. It's a right triangle, which means you can use SOHCAHTOA for your trig functions, but I'm going to do this with law of sines just because y'all seem to really like that. So I have the sum of force and the net force, which is what I want, and the angle across from it is 17.5. So I'm going to divide that by the sine of 17.5, and that's going to equal, and the only other side I know is weight, so it's going to be 68.6 newtons, and the angle across from that happens to be 90, which is really nice. Okay, and so I'm going to solve for the sum of force by multiplying both sides by sine of 17.5, and I get that the net force is 20.63. So that's nice. I'm going to go all the way back here, right, because I want acceleration at the very end. So I'm going to use 20.63 equals 7 kilograms, which is my mass, and that's given to you in the problem, times A. You divide both sides by 7, and you get A is 2.95 meters per second squared. Yay! Yay. That's only half of the problem, though. So for B, I'm going to leave that for you on your own because I can't do everything for you, because then what are you going to do in the next hour or so of class? So B is on your own. My hint, though, is that you need to use guess and assume that the initial velocity is 0 and the initial position is 0, because you're just going to start it from the top of the ramp and then go. And then use one of your equations from the beginning of the year. Okay, so for the rest of the time, I want you to work on homework 2.3. It will be due on Wednesday when I hopefully am back, and we'll spend some time going over it at the beginning, but I'm not going to obviously go over every single one, and there's not going to be enough time for you to do it, so you need to do most of it today. Number 6 is tricky, but I know you can do it because you now have enough knowledge to go ahead and do it. So the one hint I want to give you is that you need to draw 2 force maps, one for each block. Anytime that you see multiple blocks, you're probably going to need to draw force maps for every block. And of course, help each other out. I know that in every class there is at least a handful of people that understand and can learn from a video. So if you are one of those that really understands, please be a team player and help those out who are freaking out and panicking and don't learn as well from videos. So and I'll see you soon, hopefully, and Have a great Monday.